Matrixology. All right, so we are starting off this series of web lectures, and I'm going to put in as much, stick to theory mostly, and give a few examples as we go through. And the way this course works is you could find out everything from online, and in classes we go through problems in detail. So hopefully it's a good general resource. Just so we know, matrixology is fantastic, and you will come to believe it. So there's sort of there's a narrative arc to the course, really, and AX equals B is our friend, right? So this guy here, matrix times a vector equals a vector, and usually the story, so this will change a little bit, but usually the story is we know what A is, and we know what B is, and we have to figure out what X is. That's our game. Right? So the simplest example, and I'll just put some other pieces here and get rid of them, is, let's say, 2x equals 4, right? Too hard for Stephen Colbert, but there you go. That's simple, right? So we would divide through by 2. If we could divide through by this matrix, which we haven't really talked about yet, but if we could do that. So this is sort of some just generalization of that. That's what we're doing. And if you like, you can start to think of these guys here as A is a set of building blocks. So A contains building blocks. B is some real thing you're trying to represent. So it could be the sound of an orchestra. And A is the musical instruments. And X is how you combine them, right? So if you like the volume of these things. So, right, let's just get on with it. We're going to talk about something that people may have seen in 8th grade. It's something that appears early on, and then there's this talk of matrices sometimes, but it can disappear. Incredibly important area, right? So you have matrixology or linear algebra and calculus. These two things are unbelievably important. And the more and more we get into algorithmic worlds, right, that's sort of the evolution of things, the more we need discrete mathematics. And linear algebra is foundational. Okay, so the first thing we're going to start with is just identifying these. There are 3 ways of thinking about these AX equals B problems. The row picture, the column picture, and the matrix picture. And I'll just illustrate a couple of those. All right, so our example as we go through is going to be very simple, equals 1. Let me blow this up. And we would call this, right, it's quite simple. You could play around, figure this out in different ways, but we're going to give you a very systematic way of doing it with the so-called column picture, right? That's going to be the way to. So this is a system. It's a collection, a system of linear equations. Right? They're equations. Something equals something. They're linear because we just have things like 2 times x1, and implicitly it's not really said here, but there's a 1 here, 1 times x, and that'll be important, and a 1 times x2. Right, they're linear. There's no x squareds or anything like that. We won't use x, y, z's or x, y, z's. We'll just use x1s, x2s, x3s because we're very happy to have x73, potentially incredibly large systems. So this is a 2 by 2 system, right? So it's a 2 by 2 system, and the way this is m, and this is n. We'll always write m by n, and if we go back up here, we have an m by n matrix. Again, all these things will be clear. This is an m by 1 vector, and this is an m by 1 vector here. So if you have a box, right, m is the measure down this side, it's the number of entries this side. So it's all about numbers in boxes. There are m rows and n columns. That's the way we think about this. And these pieces must always match if we're going to multiply 2 together. So we're going, I'll repeat a lot of these things. We're going to get into that properly. I haven't even defined how to multiply these guys. So these are going to be n columns and m rows, right? So number of equations is rows, columns is the number of variables. So let's write that as well. Equals the number of variables. Because it's 2 by 2, it's not clear yet. And we'll work a lot with 3 by 3s and 2 by 3s and so on, because once you get to 3 by 3, you get enough complications. This is a course where we don't do terrible algebra, really. This is all about understanding, right? Because eventually you get a computer to do everything. I mean, eventually they'll get us to do everything too. But in the meantime, we're in charge. So m rows, that's the number of equations. Okay, so this is just a little bit of anatomy of this system problem. So I'm sure you can plot these equations, yeah? Even I can do that. So x1, I can use a ruler. Right, so there's x1 and x2 here. And the first equation, which we haven't really labeled, but it's equation 1, passes through. So it's going to be here, there's a 1 here. It's got a slope of 1. So it's going up through here. Let's give it a different color. Great. Exciting. Excellent device, right? So this one is, minus x1 plus x2 equals 1. So we'll just draw them roughly. The next one crosses at 2 here and 4 up here. So I've drawn that somewhat badly. So that's an attempt to draw a line. Okay. Yeah, so this is 2x1 plus x2 equals 4. Good. You can kind of eyeball this and say, oh, it looks like it's going to hit at 1 or 2. There'll be a lot of nice integer results. Because again, I'm not trying to tax your algebra. It matters. You must have fantastic algebra. We're trying to get through understanding here. So from this you can see there's one solution, right? These equations are both true at one point. So there's one solution. One solution to this system, right? One unique solution. We'll talk about that's a very, very important aspect. So what we'll find out is there can be, I'm not going to have, there are going to be plenty of spoilers. Let's do it like that. 0 solutions, one solution, or infinitely many. I'll repeat myself again. So the normal way of doing this is we would label these guys. We'd say, all right, this is equation 1, this is equation 2, and we'd just do some, so the sort of traditional way of doing this, usual way of solving, right, is we add and subtract things, yeah? So we'd say, just write them out again here, equals 1, and then get it nicely cleaned up. And then we'd say, okay, well, if we took 2 times the first one, right, so if you see this, if we take 2 of this guy and then we add it to this one, we'd be able to get rid of it, we'd be able to cancel these 2 out. So that's a strategy that we're going to generalize, right? We're going to use this. So we'll write down what we do. So equation 3, this is our new equation. It's going to be equation 2 plus, very excitingly, 2 times equation 1. So we'll do that. So this is our new equation. So we're going to add those 2 together. 2 times the first one. So that gets rid of that guy, as we said. And we'll get a 3x2, right? So there's a 2 times x2 here and a plus 1x2. Add them together. Get 3x2. 2 times this one plus 4 times this one. Plus 4 gives us 6. And so this is equation 3. And so this, from here, we're like, oh, this is good, this is fine, no problem, right? So we can see x2 equals 2. So this is a very important thing. Usually you find one of the solutions, and then we figure out, we go back and figure out the others, right? We could have, again, many, many solutions. Many, many variables. So substitute into equation 1. Doesn't really matter because both equations should work. So substitute into equation 1. It's not a serious calculation, so we can keep the goggles up. So this is 2, put it in here, right? Take it to the other side, so we've got minus x1 equals minus 1, right? So minus x1 plus 2 equals 1. Move that around, we'll end up with x1 equals 1. So our solution is this, x, and I'm going to start writing this, x vector equals x1, x2. We like to put all our vectors are columns, right? Unless we indicate they're not, right? That's the default. If you see a vector, it's a column. We'll talk about row versions later on. Again, there's always more later in this course. It's great. Okay, really awesome. All right, so 1 and 2. And that's with this little crude drawing, that's roughly what we got. Okay, so that would be great, right? We found the intersection of two lines. So there's just a few little notes. We found intersection of two lines, right? Both of them are true, right? So both equations are true at one point. Are true at this one point. Okay, good. So this is a beautiful thing. Algebra, because this was just a little bit of algebra, but back and forth with geometry, right? So our intuition, right? We can machine out the left-hand side here, but this is good for us, right? If we can make a picture of it, yes. We like that, right? Good. Other possibilities are, so we could have had this, right? So we could have had, so that's good. Other possibilities, well, let's see. Let's say this. In fact, there are not other, but I'll just say that there are 3 possibilities in this case, right? For these having two lines. So we could have that there's one solution, right? So this is A, so they hit at one point. One solution. They could be parallel, like this. This is B. No solution, right? And C, very excitingly, they could be the same line. So they're parallel and the same line. I guess I put the B's and C's in the wrong. Okay, so and in this case, there are infinitely many solutions. Right, so only 3 numbers matter, 0, 1, and infinity, which is true in general. Okay, so this is called, let's go back and give this a name. This is the row picture. Because we're thinking about rows. The equations are rows. So now let's do what is the column picture, called the column picture, and this will be much more powerful for us. Matrix picture is awesome as well, and that takes the whole course to figure out how that works. Yeah. So we could rewrite this problem. So we're going to rewrite the system this is where we start to get into matrices a little bit in this way. So we could put x1 and we'll put a vector here. Right, there's a -1 and a 2 plus x2 times 1, 1 equals 1, 4. Now this is a big deal. Big deal. So now we've got a different story. We're saying, well, here's a vector, -1, 2. How much do we multiply that by, and how much do we multiply this 1, 1 vector by, and then add them together to get 1, 4, right? So this is a target now. This is our B vector. Awesome. So these are our building blocks. They're the columns. They'll be the columns of A when we fix that up. Good. And this is a different story now. We're in a different space. Over here we're in x1, x2 space. Now we're just going to give it a different label. We've had y sitting around, so we haven't used y, so we can use y now. It'll take us a while to understand what this y space is, but that's okay. So I'm going to call these vectors, let's give them special names. This is A1, and this is A2. All right, so something times A1, fixed vector, plus something times A2, to dial them to get 1, 4. Yes. Right? The course is just filled with this. All right. This is the intuition, anyway. Okay, so good. All right, so we're going to do this. These are our building blocks. So let's draw in our little building blocks. There's this one here. This is 1, 1. Right, this is A1. No, it's A2. That's A2, yep. And minus 1, 2, so that's out in this direction. Let's call this 1 here. This is minus 1, 2, right? Minus 1 across, 2 up. This is A2. Good. Okay, so we could add these together in some way, and with multiples of them, to get what we want is 1, 4. So 1, 4 is up, let's say here. This is our thing we're trying to make, right? So this is going to be two instruments. They make a sound. We're trying to make a combined sound. And we have to solve this problem again. Now we know from the previous one, we had 1 and 2, right? So from before, from that row problem, we have x1 equals 1 and x2 equals 2. All right, so we have one of this guy, one of the, let me do it like this. There's one of this one and 2 of these. So let's do that. We'll make it, this one's like this. We're going to extend it out here. This is 2 times A2. And this is, it goes all the way here. This is 2, this is just A1. 1 times A1. And if we add them together, we get B, right? So B is 1 times A1 plus 2 times A2. It's exciting, right? Somehow this will help us understand how to break pictures down, how Google works, all sorts of things, right? It's pretty peculiar. Fibonacci numbers. Yeah, very strange. Machine learning, it's all based on this stuff. Okay, so we really like this column picture because it's intuitive. If we had really big spaces, right, we can't understand anything beyond 4 dimensions, beyond 3 dimensions, right? Our brain just goes pop. Then the column picture is okay because it's just these big collections of numbers and we're dialing them so that we try to get this vector at the end. The row picture becomes harder, right? Because the row picture, they're lines in 2 dimensions, that's what we've looked at. Then they're planes in 3 dimensions. Then they're hyperplanes in 17 dimensions, and that starts to hurt. So, okay, last thing for this to say is there are again we can see why there are 3 solutions, right? So let's enumerate why that works just in general. So 3 possibilities, and again, this is just in this sort of 2 vectors situation, but this will all generalize. So A1 could be parallel to A2 and could be parallel to B, right? So they all point in the same direction. So boom, boom, boom. And then you can see how it's easy to, right, you can just choose one of the A1s and dial it. You could use both, you can dial them. So this actually translates into infinitely many solutions. All right, so there's that. So we had that one before. There's A1 is not parallel to A2. Right, so they're just not parallel. So they're askew. And that means we can combine them, right? And the ones that we like to use are I hat and J hat, right, in 2 dimensions, which is sort of the calculus terminology. Calculus is evil, so we're not going to use that. So that's a 1 solution situation. This means we can always make B. Right, so whatever B can always make B in one way, right? There's only one way only. You can always do it, but there's only one solution. And then, so this is A, B, and C. And the last one is that A1 is, again, parallel to A2, but they're pointed in a different direction to B. Okay, let me put some things in here. So this is maybe A1 and A2, and B is in a different direction. And then in this case, we've got A1 and A2. They're pointing here, and B is over here. So let me make B slightly more interesting. So B is, say, here. Right? So there's no way you can dial these guys up and down to get B. Right? It's impossible. So there are zero solutions. I've gone to the wrong place. 0 solutions. All right, so let's go back to this. So 0 solutions. All right, so that's that's a big story for us, right? That gets us a long, long way. All right, good. Matrix multiplication is the next thing to think about here. We'll talk about just a little bit. We come back to it. So the matrix picture, right? So this is going to be the matrix picture, which is in the end where we get all sorts of understanding, because right? So we've got AX equals B. That's supposed to be the core of all of this. AX equals B, right? Matrix, right? So it's again an m by n matrix in general, m by n. This is, it's no good. In fact, let me do this. This is an m by n, m by 1, and an m by 1. You just need to drill that in, right? So it's m rows, n columns. It's easy to lose track of that, but just get that in, because we're doing training here, people, just training. Okay, so matrix multiplication. So we said these things are the same. So let's kind of get these out in two different ways. So I'm going to just tell you that if we started with, this is our system, 1, 2, 1, x1. And I know we're jumping things a little bit. If you haven't seen matrix multiplication, I'll just tell you how it works. So, so this is equivalent, right? This is what we had before. So this is the matrix picture here. So let's see. Let's get so there are two ways to multiply. There are more than this, but two useful ways here to multiply matrices. There's the basic way. Okay, so one, we're going to do dot products of rows and columns, right? So dot products of rows and columns. Again, we'll come back to it. So we'll have this, that we have rows, right? So minus 1, 2, 1, x1, x2. Take this dot product, and right, so we're going to take, let me do this, dot product of these, right, this row vector and column vector. Right, so if we do that, we get minus x1, oops, minus x1 plus x2, right? So there's minus 1 times x1 plus 1 times x2. And then, so this is the calculus thing. And then 2, so the next dot product is 2 times x1 plus x2. Now the important thing to see here is that this is, well, one of the important things, this is our 2 by 2 matrix, A. This is our 2 by 1. These guys connect. This is actually a 2 by 1 as well, right? These things are adding together, they're stacking together. Now all of this we had equals B, so in this case it's 1, 4. So we're going to equate these two things, right? So let me connect it like this. So these guys are the same, these guys are the same. So that gives us our row picture. So the row picture pops out. Good, right? Minus x1 plus x2. X2 equals 1, and 2x1 plus x2 equals 4. Okay, so that's one way, and what we can do is, everything with matrix multiplication builds from that, from these dot products of rows and columns. If you think about it, you can see that there are ways to do it with kind of a building block approach. So we could think about, so maybe think about it like this. Take objects within objects, right? So matrices within matrices. So let's say this is really two vectors, two column vectors. 1, 1. This is the same thing, right? So this is kind of a row vector, right? It's really a 1 by 2. And the objects inside it are themselves matrices, but it's a row vector. So, all right, so if we had that, so there's now just one row. And if we take that dot product, then there's x1 times this plus x2 times this guy, just a dot product, just with slightly more complicated objects. And you can see that this all follows from the original definition, right? So I'm going to put the x1 in front because it's nice. 2 plus x2 times 1, 1. And again, this equals 1, 4. And this is our column picture, right? Pretty awesome. So they're equivalent. The second way, the column picture, is the way we like to understand things. It's a good way to understand things. So this is good for intuition. Again, the row picture is actually how we will solve it, though. So when we go back, this initial way of solving things here, right? We'll have a very stylized, formalized version of how to do that. Right, so it's called Gauss-Jordan or Gaussian elimination. We will get to that. I think that's pretty good. We can move to larger and larger examples later, but I think that's sort of a quick introduction. So we're really focused on this AX equals B business. This is a big deal to us. This thing here, that is really what we'll work on for much of the semester, which doesn't seem like too much. But the first third will be about solving it. The next third will be about expanding our understanding of how the mechanics of AX equals B works. We're going to get this so-called big picture into us. Then we'll have an excursion into eigen stuff world, which is amazing. And that will again come back and inform AX equals B at the end. All right, good place to start for this first little introduction. All right, onwards.